Good evening. We are Alex, Heidi, Jesus, and Frank of table number 2. We are here to talk about our water balloon launcher project. The main objective is to hit a target which has a distance of 15 to 25 meters. To do this, we will determine a couple things. First, what do we know and don't know? For our knowns, we have here of our mass, which equals 0.25 kilograms for every water balloon. The angle at which we have is 45 degrees for that slingshot. The distance we already know, and then gravity is negative 9.8 meters per second squared. Now what we need to find is x bar, which equals our stretch length, k, which equals our spring constant, and then the most important thing that we need to find is our equation of x bar when given a distance. Second, how can we find it? And then by doing that, we are going to use an energy model. Then we go on to using vectors, and then finally kinematics to solve that.
So to find our spring constant, we set our force elastic equation equal to Fe is equal to negative kx bar. We ran 3 different trials using our launcher and a Newton meter. The 3 trials measured at 3 different stretch lengths. We found an average spring constant of 105.45. We then constructed our LOL energy models, and we set our initial position at right before we launched our water balloon and our final position as just as it is about to hit our target. We assume that at both positions H was equal to 0, and at the beginning all our energy was E internal due to the high value of K. We assume that this was a closed system because we are neglecting air resistance. Thus, all of our E internal was converted to E kinetic. So we set our E internal equal to EK, and we're able to construct a velocity equation of V equals 20.5 x bar.
After we found our velocity using the LO energy diagram, we simply use vectors and SOHCAHTOA to find the components of the velocity. We use cosine of 45 times our velocity to find Vx, which was 14.5 times x bar, and sine of 45 times velocity to find in the Vy. After we found our components, we compare our original K value, our average K value of 105.45 to with 3 launches we did with the tracker program, and it gave us these values, which averaged out to 145.81.
So second to that, next what we do is that we set equal 2 velocities together, and which is an example is what we have here, which we got from this velocity here, and then this one we got from the vector right here. So we set equal to that, and then we solve for k, and again we find the average of being 145.81.
The difference of average K values could be due to a wide variety of variables such as time of launcher's use, launcher stiffness is not so constant. Also, a tracker program couldn't measure exactly what the center of mass of the balloon was each time.
Okay, so now we know a couple of things. We know our average K value, we got our velocity of X direction, and then our velocity on the Y direction. Next, we use kinematics model to answer our final question. How do we find stretch length? So we arrange the direction of motion into its X component and Y component. And the X component of motion is equal to 0, assuming that air resistance is negligible. This will give us a constant velocity, which we know is positive from the vector method and is equivalent to 14.5 times the stretch length. We know that the area under the velocity graph is equal to base times height, which will be time times delta V. And delta V equals 14.5 times the stretch length. So if delta P equals distance, and delta P also equals 14.5 times the stretch length times time, then distance equals 14.5 times the stretch length times time. In the Y direction, we know that gravity, which is 9.8 meters per second squared, it's acting on the object constantly in the negative direction. We also know that the area under the acceleration graph equals change in velocity, or delta V. So delta V equals base 1/2 times height 9.8 meters per second squared. Delta Vy equal to 9.8 1/2 times time. And we know that delta V is also equal to 14.5 times the stretch length, which equals this 9.8 1/2 times time. Solving for t, we get 2.96 times the stretch length. We plug this into our original equation here, and we get that the stretch length equals the square root of distance divided by 42.9. By inputting that target distance as d into this equation, we should be able to mathematically define a stretch length and successfully hit the target.